Ghazal Tayebirad. So she got, she studied for the master at Tehran, and then she was to Heidelberg University, and she got a PhD just 3 months ago with Sandro Weinberger. And today she will give a seminar about engineering, Landau-Zener tunneling of ultra-cold atoms in tilted lattices. And she will be here all today and tomorrow morning. So if anyone is interested in speaking with her, just tell me anything.
Okay. Thanks very much for inviting me. Welcome to my talk. As Roberto said, I'm going to talk about Landau-Zener tunneling. So this is basically what I'm going to present is a summary of what I did during my PhD. And we studied the Landau-Zener tunneling for Wange-Stock system. The Wange-Stock system basically is the problem of dynamics of electrons in periodic structure, where you have an extra electromagnetic field which makes the electron to move there. But this Wange-Stock system can be very well realized by ultra-cold atoms forming a BoseEinstein condensate in optical lattices. And there we have a constant force, a static force, which makes the optical lattice tilted and therefore makes the atoms move. So why ultra-cold atoms in optical lattice? Because it provides an optimal possibility to have a very well controlled, experimental control on different parameters by optical means, and these lead us to use them as a toy model. Sorry. Okay. Why it doesn't move? No idea. I tried, but it was working. Sorry.
Maria Antonia was because it was broadcasting also a presentation, so maybe this is interfering with the transition of the slides. That's bad.
Maybe when we have time, I would like to ask you,
yes.
Because we talk about somehow electrons that in the type with atoms. So what do you mean really?
Sorry, I talked about.
You mentioned electrons somehow.
No, I said originally the Wange-Stock system is the problem in the condensed matter physics for electron transporting periodic structure. But this system, basically, I will show you in the next slide, but these systems are not clean enough, so they are very difficult to have a control on different parameters. So people in atomic physics and optic physics, they came together and then they found this system, optical system. So this is a toy model, very similar to condensed matter physics phenomena, but we have a very good control on different parameters here. So this is a similar problem to electrons in structure.
And this is theoretical or?
This is both. I mean, I have done theoretical works, but in collaboration with experimentalists. So experimentally is very much visible.
And tilted lattice, you mean, so you have a space, some coordinate system, and you change angle or whatever?
Yes, so we have some periodic lattice, which I tell you in a minute how. And then either similar to the electric field you have for the electrons, we have also a force, and we have it like with different angles, we can control it.
We just, Maria Antonia is checking something. So did you check before to connect this?
Yes,
it was working.
yes, it works, yeah.
So
Maybe I should have started.
That's probably the best thing to do.
But not it's in the 9 hour months. The problem is I don't have a control. What did you do? I don't know. It just eventually
maybe
started
we
to work.
should change something. Okay.
Okay. Okay. So we're starting.
I think the introduction was with the question.
Yeah, well, he wanted the whole talk in 3 seconds. So.
Okay, now we see what is BoseEinstein condensate. So BoseEinstein condensate is a collection of bosonic atoms confined in the harmonic trap. So a trap which is given by the harmonic oscillator and then cooled down to the very low temperature with different technique called evaporating or the laser cooling, and actually that's very similar mechanism when your cup of coffee goes cold. So when the atoms are cooled down, they just go to the lower levels and they all occupy the ground state of the harmonic trap. So therefore we have a macroscopic wave function all occupying the same quantum states. And this has been observed experimentally in 1995. As you see here in this picture, you see the momentum distribution or the velocity distribution of this pack of the quantum gas. And as the temperature goes down to a few tenths of nanokelvin, we have a very nice narrow peak in the momentum distribution, and this will be actually the characteristic. So this is the Bose-Einstein condensate, and that's the important part because this is the advantage to have a control. So first of all, we can control this narrow peak, have a very narrow peak. Second, it gives us the possibility to have dynamics in the system and then study the dynamics. And then it led to the Nobel Prize in 2001, a joint Nobel Prize with these 3 groups. Okay, then I said that we load the Bose-Einstein condensate in optical lattices. The optical lattice can be created by 2 counterpropagating laser beam, as a similar picture you see here, and the standing wave, which is created by this optical lattice, is called, by these laser beams, is called optical lattices. So we have such a periodic structure, and the lattice constant and the depth of the lattice can be controlled very well by optical means that if you change the intensity of the laser, you can change the amplitude of the lattice, and if you change the frequency, you can change, the wavelength, you can change the lattice constant for your optical lattice. And here is the potential, and we can make it 1 dimension, 2 dimension, or 3 dimension. In this talk, I will concentrate on the 1 dimension case, and it is again possible experimentally by using confinement. So you confine the system in 2 directions and then only have a very, very broad confinement in each direction. So therefore you have transport in 1 direction and no transport in the other directions. Okay, and then as I mentioned in the beginning, so this system in the atomic physics are analogous to the condensed matter physics when you have electron in crystal, and similar phenomena can be seen as predicted for the condensed matter physics. Now it can be seen in atomic physics. And the condensed matter physics, there's a difficulty that you don't have an optimal control on the parameters. You have impurities, you have unclean system. So it avoids observing many interesting phenomena. In this system, however, we have a clean setup and control very well every parameter so that we can observe the phenomena which was predicted there. So they call basically this system as a quantum simulator because it makes us able to see the phenomena from the condensed matter physics. Okay, so there I come to the outline. So using the Bose-Einstein condensate in optical lattices, I introduced the Vanier-Stokes system, and I show you how we study the dynamics in the Vanier-Stokes system, and then I show you the Landau-Zener tunneling in such a Vanier-Stokes system, and I present different possibilities to control the tunneling. Then I go beyond this system and I introduce disorder, so I have a time-dependent stochastic potential, and now the question arises whether we are able to control the tunnelings in such a time-dependent stochastic potential. I show you the results, and then at the end I introduce another type of potential as a benchmark. I should mention that since I mentioned that everything is very well controllable in experiments, so we did a collaboration with the experimentalists, and part of the talk, basically the first part, you will see results from experimental group of the Elio Arimondo in Pisa, and you will see how they agree with each other. Okay, so we loaded the BoseEinstein condensate in optical lattice. Therefore, we have a periodic system, and I should say that the BoseEinstein condensate can be prepared with a negligible interaction. So for the moment, you see that there is no interaction term. We have a simple periodic Hamiltonian, and the solution to this periodic Hamiltonian are known. They are Bloch waves with a band structure. And here you can see only the first two bands, the band structure. And our system has been prepared with a narrow momentum distribution at the center of the Bernoulli zone. And again, I remind you, this is the advantage of using the BoseEinstein condensate, because I show you this nice peak that it has a very narrow momentum distribution, and that's why we can have a narrow wave packet within the Bernoulli zone. So then, it is possible experimentally through the frequency difference, theoretically by adding a constant force, a static force, to a system to have this optical lattice now tilted, and therefore the dynamics of such a problem is described by the Wannier-Stock Hamiltonian. This is the Wannier-Stock Hamiltonian, and this is the third term arises because of the static force I added to the optical lattice. Now we have the wave packet due to this periodic system within the Brilliant zone. Then we turn on the force, so it starts to move between the Brilliant zone, and then at the edge of the Brilliant zone, part of the wave packet reflected and gives rise to the phenomenon called Bloch oscillation, with the Bloch period inversely proportional to the force. And then the rest part of the wave packet can tunnel to the higher band through the first band gap, because the band gap basically at the edge of the Brilliant zone had its minimal value, so therefore there's a probability of tunneling to higher bands. And then the wave packet which tunneled up just scaled from the system through the successive tunneling across the much smaller band gaps between the upper bands. So we have the full band structure, it's not just the two bands. It's not a closed system. Okay, so since we have tunneling to higher bands, therefore the population in the ground band is decaying. And the Landau-Zener theory predicts the decay rate to be exponentially proportional to the band gap square and inverse of the force. And then we have also the periodicity multiplied to this exponential expression. Okay, now the question is whether this is the whole story. Do we see an exponential decay when we have tunneling to higher bands, or we can see some other structure? And to check that, we look at the time resolved probability of the condensate to remain in the ground band which we initially prepared it there. And such a survival probability is very well measured in momentum space by projecting the evolved state onto the support of the initial state. So here you can see the time evolution of the survival probability for 3 Bloch period. You can see that both numerical results and the experimental results shows a nice step structure for the survival probability. And why a step structure appears exactly goes back to what I explained before. That's because we have the wave packet moving for half a Bloch period, for half a Brilliant zone, therefore we are in the ground band, and then at the edge we have tunneling, we have decay of the survival probability, and then we sweep again the whole Brilliant zone, therefore we have the whole Bloch period here, and then again at the edge we have tunneling to higher bands and so on. Okay.
These are numerical simulations of the running equation? Simple.
Yes, yes. Exactly the Manish Hamiltonian I showed you before.
And in the experiment, you have the condensate and then you do the lattice when you start to.
Yes, you prepare the condensate, then you ramp up the lattice adiabatically so that the condensate stays in the ground band, and then
you have the
acceleration.
Okay.
I mean, experimentally, they really don't tilt it. They have some frequency difference between the two laser beams, and therefore the standing wave is moving. So it's a relative movement. So in theory, we consider that the atoms are moving, but in experiment, basically the lattice is moving with respect to the atoms.
So actually, the return will differ, will be time dependent.
Yes, if you exactly, and if you do the Lorentz transformation, the time dependence in the lattice goes back
yes,
out, and then gives you the linear term as a character. Okay, and this, so the dashed line is basically the Landau-Zener prediction, which was the exponential. So this is the exponential line. And you see that because of the step structure, we have deviation from the Landau-Zener prediction. And that's because we are able to look at the time evolution of the survival probability. As I just remind you, the Landau-Zener prediction is a time-independent expression, which gives you only the asymptotic value. Okay. Then I characterize each step with the height and the width for each of the steps. Now, in order to see whether the Landau-Zener tunneling probability, the predicted probability, gives us the correct height of each step, or basically one single Landau-Zener crossing, we studied a single transition, only one step of the survival probability for various value of the lattice step, this V0. And here you can see again the survival probability as a function of time for only one Bloch period. You see that by increasing the lattice depth, when you have a deeper lattice, you have suppression of tunneling, so less decay of the survival probability. And then when you have a shallower lattice, you have more decay of the survival probability, which means that more tunneling to higher bands. Okay, now I just feed the survival probability, the steps by a step function you see here, and I just extract the height of the steps as an h, and I compare it to the Landau-Zener prediction. So again, I just forgot to say that these are experimental results, the symbols, and the lines are my numerical results. And here you see the dashed line given by the Landau-Zener theory, and the numerical results by blue squares and circles are experimental results. We just plotted the height of the steps for various value of V0 square over F, because the same story happens changing the force in the system. So if you have a larger static force, you have more tunneling and so on. Okay, so we see the same exponential behavior for the height of the steps.
Theory is again the numerical solution.
Yes. So the theory is a Landau-Zener theory.
Oh, Landau-Zener.
Numerical is
okay.
Now, just before going to the, I mentioned that there is a second characteristic for this step, and that's the width of the steps. It is possible to control the width of the steps changing the initial condition. What was the initial condition? Is basically the initial width of the wave packet. So if you have a narrow momentum distribution initially, then you see a nice step structure I showed you in the beginning. If you prepare the condensate with the broad momentum distribution, then we start to deviate from the sharpest step structure we had, but the steps gets very smooth, and again agreement between the numerical result by solid lines and the experimental result by the symbol.
What are the experimentalists there in the list? Who are the...
So the leader is Ennio Arimondo, and then they have Oliver Morsch, researcher, and the rest are the group members. Okay.
So if the lasers are switched on instantaneously?
So you mean for the optical lens?
For the optical lens.
No, it's very adiabatic process. It's not just abruptly. Because then you excite the atoms. You have to do it adiabatically so that they stay on the
So
ground.
you have the condensate and then you switch on the lasers smoothly.
Right. Okay. Still, just to remind you that we have deviation from exponential decay due to the remnant of the steps. But if you prepare the condensate with a very much broader momentum distribution, basically it's not going to be BoseEinstein condensate anymore, it's a thermal gas because it has higher temperature, then you can reach the exponential line. And this has been done actually some years ago in the group of Mark Raisin in the USA.
Do you have any idea why there are so strong deviation from the error bar? I mean, the one with the larger error bar, and then you see the nearest point, zero error bar.
Well,
just not plotted, or?
These visual experimental is how they have it, but they usually have this shot-to-shot error bar. So they have to basically how they calculate this is just they let the condensate evolve, then they switch off everything, let the condensate just drop down, or they call it time of flight. And then they measure the momentum distribution. So therefore there might be errors always in the measuring, and this error since each point is calculated separately in different experimental setups, okay. So they can be different. Okay. So up to now, I showed you all the results in the basis of the full Hamiltonian, of the vanished Hamiltonian, which is called adiabatic basis. But we are able to experimentally, also numerically, using different protocols, and then do the calculation in other bases. Just to see what is the effect of another basis. So here we use we did the calculation in the diabatic basis, which is the basis of unperturbed free particle wave function, so when you don't have any coupling between the bands. And then we looked at the same observable, the survival probability, now doing the measurement in diabatic basis as a function of time. You see that for a single transition, previously we had a smooth step, but now we have a second time scale appears, so the oscillation appears on top of each steps, and very strong oscillations compared to the adiabatic case. And this can be seen very nice experimentally also, as you see by the symbols. And this shows us that just doing the calculation, first of all, we are able to do in whichever basis we are able to do calculation in whichever basis we like, experimentally and numerically. Second, we see that still we have deviation from the exponential, even more deviation from exponential prediction due to new time scale in the system. And
these experimental results don't look the same as the previous transparency. These are new conditions?
Yes, they have a new protocol now. Basically now they turn off everything, so they turn off the lattice at the end, and then they look at the distribution. In the previous case, they have to, they don't turn off everything suddenly. They ramp up the lattice again, they separate the excited states and the ground state, and then they look at the population in the ground band. So I don't know if I could make it clear, but basically the protocols are different. In this case, for each point they turn off everything and they let it project on this unperturbed preparticle state. In the previous case, they changed the amplitude of the lattice so that there is no tunneling happens anymore, and the tunnel part just gets separated from the untunneled part, and then they turn off everything and they look at only the ground population.
Diabatic versus adiabatic basis refers to breaking of the Born-Oppenheimer approximation, or like in molecular dynamics, or here it has a different meaning?
Here the diabatic basis would be only the basis of the diagonalized Hamiltonian, so when you don't have any coupling. I don't know exactly if this is similar to what you mentioned. But
well, in molecular physics, I mean, adiabatic is the usual, Born-Oppenheimer approximation. Nuclear are fixed, while diabatic is when you have a strong coupling with this electron and nuclear, because of motion or
different distribution. Okay, now I just so as I mentioned in the beginning, we have the system is analogous to the electron in periodic distortion, and in the condensed matter physics, interaction is very much important. Now, in order to get closer to the real system, we consider the impact of atom-atom interaction. And now we have a dilute gas with a weakly interacting atoms, and in such a system, the dynamics can be described in the mean field regime by using the Gross-Petrovsky equation. And what makes this equation different from the Schrödinger equation is basically this fourth term, which is the nonlinearity term. And the nonlinearity is given by the coupling constant G, given by the S-wave scattering wavelength, and the number of the atoms in the condensate, and also the peak density. Okay, now, just to make it easier for the next slide to show you the amount of the nonlinearity, I use a dimensionless nonlinearity. We call it C, and that's only the density of the peak of the condensate divided by the recoil energy, the energy scale of the system. So we just introduce some dimensionless nonlinearity. And if you look at now the observable we had before, the survival probability, we see some deviation from what we had previously. So the black curve shows the linear system without any interaction as we had before, and you see a sequence of Landau-Zener tunneling process. Now, if you consider interaction in the system, as the strength of the interaction increase from red to blue, you see that we have a deviation from this linear case. We have enhancement of the tunneling, we have more decay of the survival probability. We see that the step structure just washed out because the nonlinearity start to destroy the coherence in the system, and the Bloch oscillation are just vanishing. And third, we have also, I cannot show it here properly, but if you consider that here we have an exponential line of the prediction of Landau-Zener, in the interacting case, we are not able to define a global exponential line, but it's defined only locally in time, which means that the line is changing its slope during the time. And the reason is the density in the wave packet is changing in time since you have tunneling to higher bands. So your density, which you use in the nonlinear term, here is changing after each tunneling events, and that leads to different survival probability. yeah, so now basically this is still not the whole story in this system. We can again introduce another condition to the system, and this is called for example, a resonantly enhanced tunneling condition. And that happens when the energy induced by the force matches the energy difference between the initial state and the final state. And this leads to a resonance in tunneling process. And this is called, again, a resonantly enhanced tunneling, has been observed also experimentally, as predicted also theoretically. And in this case, this is actually, again, another deviation from the Landau-Zener prediction, because Landau-Zener is not valid for such a resonance case. Again, the opposite case will be the case that we don't have the resonantly enhanced tunneling, which means that the energy induced by force doesn't match the energy gap. And this is the case where Landau-Zener is valid. Looking at the decay rate of the survival probability in the presence of interaction for various amount of the force, you see that first for the linear case given by this theoretical calculation, the solid lines in the both figures, we have a peak appearing at some values of the force, which means that some values of the force leads to enhancement in the transition. Then you increase the nonlinearity, and you have this leads, as I showed in the previous, leads to overall enhancement of the tunneling. So we have, for repulsive interaction, we have more tunneling. The peaks of the resonantly enhanced tunneling are vanishing. And also theoretically, they have done work for the attractive interaction. And there they see that we have suppression of tunneling. So basically they can control the tunneling by just changing the interaction in the system. And this is the same story, only the calculation in the experiments. So these are experimental results, this is theoretical or numerical calculation. And they both show the same behavior. Okay, now, till now I just showed you an order system with the tilted periodic potential. I would like to go beyond and then introduce a second lattice with incommensurable lattice constant and the time-dependent phase for the lattice. If you add this second lattice to the previously existed one, you will have a disordered system, which is actually also time-dependent, which makes it even more complicated. And here you can see the potential, which is the initial potential, and this is the second lattice with the incommensurable lattice constant, and this makes the potential already a random potential. And so we have also a phase shift or phase difference between these two lattices, which is the time-dependent lattice.
Again, could you call that random? What is the stochastic part?
The stochastic part comes from the phase. I will tell you in a second how we define it. And it's already without this stochastic term, it's random because we have incommensurable lattice constant. So this is an irrational value.
So it's spatially random and stochastic.
Exactly. Additionally, I introduce a value called alpha, and that's a renormalization factor I introduce just to be able to compare my results from a reference system, which is the initial lattice I had, to the new potential I have consisting of two lattices, which means that I compare the standard deviation of this full potential to the standard deviation of the initial potential, and then I just calculate some normalization factor. And how this time-dependent phase is defined, basically you can have different random number generators. What we chose mostly, like we were mostly interested to use the harmonic noise which is produced using the harmonic oscillator, a damped harmonic oscillator, and driven by a Gaussian random number given by this psi.
What is capital T here?
The capital T gives you the strength of the driving, basically it's the strength of the noise. Omega is the oscillation frequency and gamma is the damping. And the variance of this harmonic noise is defined by the capital T divided by omega 0 squared.
But this noise intends to model a natural process which is already there, or is something that you apply from the outside?
We applied it. I mean, originally, if you want to consider some real system, there might be some noises there involved, but now we have it only in our lattice as a parameter that we can change.
That you control from
Yes,
the outside.
yes. Okay, since we have a random number, so a noise, therefore we need to average over several realizations of the system, and that's why I say here statistics needed. So what else is a characteristic of this harmonic noise? I mean, why we are interested in such a noise? Because if you calculate the spectral distribution is the Fourier transform of the autocorrelation function, then you get such a function, such expression, and if you plot it, it gives you two regimes. In one regime, we have a peak in the spectral distribution at some finite value of omega naught, which you can calculate it, and some finite width of this peak. And that's the regime where the oscillation frequency is larger than the damping, so you have oscillating phase. And if you have a small oscillation frequency, then you have a Lorentzian distribution, which is similar to another type of noise called exponentially correlated noise. And that only characterized by some correlation time. But I don't talk about it here. If you are interested, we can talk about it later because I have finite time. So I only consider the harmonic noise only because of this interesting spectral distribution it has because of the peak. As I mentioned, there are two different regimes. One is the slowly varying noise when you have a small oscillation frequency, and once you have a large oscillation frequency, you have a fast noise. Of course, you have to say fast compared to, like large compared to what, or small compared to what, to compare to our Bloch frequency, the frequency scale of our system. So in the first regime, compared to the total time of the observation, one can have a constant phase because it's very slowly changing in time. And in the second case, since we have a very fast changing phase, therefore we came up with an effective model, and the effective model can be calculated or can be found by integrating over all the possible phases, and then therefore the time dependence which was here in the second lattice is just integrated out, and then we have a renormalization factor for the second lattice given by the characteristic parameters of the noise. Basically, here I just remind you this is the variance of the harmonic noise. Okay, taking into account these two different regimes and looking at the observable we had in the beginning, the survival probability. Here we studied the impact of the strength of driving, the T, capital T, in the regime that we have a slowly varying noise at some variance which is defined by T over omega 0 squared. So if you first of all, this is the reference system, the normal periodic system. The colored one are the disordered systems. If you increase T, you see that from a suppression of of the survival probability, decay of the survival probability, you just make a transition to an enhancement of the decay of the survival probability. So basically, in this regime, mostly we have less decay of the survival probability, less tunneling to higher bands. Since the driving is just like you have a constant phase, and the disorder system leads to less tunneling. It's localized. Only if you have a very strong phase, you just drive the system out of the ground band, and therefore you have a lot of tunneling. But this is just this strength of the noise is just too strong, and we cannot consider anything more physical here. Okay, in the other regime, the story is a bit more interesting, and that's a regime where we had a peak in the spectral distribution. The phase was a fast oscillating phase. Therefore, we see that for all the values of t, we have enhancement of tunneling, which means that we have more decay of the survival probability. And then we were really surprised to see that, okay, the disorder system with a time-dependent phase leads us to a more tunneling to higher bands. And we started to do even more investigation just to see the impact of different parameters, and also like different parameters of the noise, also different parameters of the system. Just reminding you that we had a condition of resembling and trans-tunneling and a non-red condition. And taking in these two regime of the system parameters, we look at the survival probability in the red and the non-red case. First, we have a reference system given by the black curve, and already you see that for the red case, we have enhancement of the tunneling comparing to the non-red case. So they are both for the same lattice depth, only the force is changing. And then we use our effective model with the renormalization factor, and we see that the effective model, the survival probability in the red case lies above the survival probability in the reference system, and in the non-red case is slightly below it. Now we start to do time-dependent, use the time-dependent potential with the random phase, starting from the regime where we have a small oscillating frequency. And you see that for the non-red case, we have suppression of tunneling, and for the red and non-red, we both have suppression. Then we increase the frequency more, very close to the frequency scale of the system, and we see that for the non-red case, we have strong enhancement of tunneling, while in the red case, we don't have any enhancement. You still see the suppression. Increase it even more to a very fast oscillating phase. We see that, okay, in the red case, it just lie at the same place on top of the effective model. In the non-red case, it just goes back up and lie on top of this effective model. And this is reasonable, because the effective model was introduced already to predict the behavior of the system when we have a very fast noise. And that's why when we have a very large oscillation frequency, the results are given from the time-dependent Hamiltonian just agree with the effective model. Now, if I just, to make a little bit the story easier for the later slide, I just pick one, I make a slice there, and I just look at the survival probability at some specific time, t0, and this time should be far enough from the beginning just to be able to distinguish the differences. So here I run a scan over oscillation frequency of the noise, looking at the survival probability at time t0 for various values of the variance. of the phase, so the harmonic noise. Before I just tell you about the symbols, I tell you that the black curve, the black line, is the value of the survival probability for the reference system. The dot dash lines are the calculation from the effective model, and the symbols are from the time-dependent Hamiltonian. Now, if you look in the beginning, I mentioned something else, that we looked at our results and then we scaled the frequency by the variance of the phase, and we could see a universal behavior for various amount of the variance of the noise. And that was very interesting for us to see that all the cases shows the same behavior, no matter what the variance is. Only we have deviation from this universal behavior when we have a slowly varying noise, when we are in the regime of a constant phase. In the fast oscillating regime, you see that the symbols are getting close to the calculation from effective model, so the dot dash lines. Only here in the middle we have a dip, and that's the part that we have an enhancement in the tunneling probability. And that's a kind of a resonance here, and that happens, as you see, more or less close to 1, which is the twice of the frequency scale of the system. So twice of the frequency scale of the system is basically T Bloch half. Why we see it here, we interpreted this way. So I showed you in the beginning that I had the band structure, and there was a half a Bloch period time needed to reach to the edge of the Brilliant zone and then tunnel up. So basically the time scale you need to reach is half a Bloch period, and that's 2 omega Bloch. After that, the noise helps you to tunnel up, so you have enhancement of tunneling, and then again you need another half a Bloch period to reach another edge of the Brilliant zone in the second band. And that's why we see a dip right at 1 here. Okay, so we ran a scan over different values of like other parameter of the noise, the gamma, and we see that actually the dip happens here in this area where we have the omega 0 in this, so here it's not a scale, so it's written in 1 over T Bloch. That's why you see it on 50. If you do the correcting as I had in the previous case, then you will see that the dip happens around 1 omega to omega Bloch. And then we see that the gamma is not very much effective. I mean, of course, if you go to larger gamma, you just lose the dip you had, but in the values that we chose, like in this area, we have this dip. And here is the region that we have a slowly varying noise, we have suppression, and here is where effective model is valid. Okay, now I introduce another potential, which is a benchmark for our system. Why? So we take a deterministic time-dependent phase, and that's actually an oscillating phase, a cosine. And it has a spectral distribution given by the delta peak. And if you go to a regime of the harmonic noise where the spectral distribution is very high and has a narrow width of the peak, then these two spectral distributions are comparable. That's why we chose this deterministic phase as a benchmark. Okay, now, therefore the potential is now defined as the following here, and the effective model can be again defined by integrating over one period of this phase. And at the end, you end up having, again, a time-independent potential with the Bessel function as a normalization factor. So this is the beta I had in the harmonic case. So we were really interested to see, okay, now we have a Bessel function. Do we see the trace of the Bessel function in an observable? So we look at the survival probability again at time t0, and we ran a scan over the amplitude of the harmonic phase. Looking at the time-dependent potential, the first equation I showed you at the very large oscillation frequency, you get the blue curves, the blue symbols, and then the effective model agree very well to the blue curves given by these magenta stars. And if you compare to the sorry, this should not be survival. This is a Bessel function. If you look at the Bessel function, you have such an oscillation in the Bessel function happens at some specific values of AD. And if you look at the structure here, you see that exactly the same deep points happens at the same values of the AD. So we can follow the trace of the Bessel function. Of course, they cannot be totally the same because this is the survival probability, and it should not be necessarily as the Bessel function. Like that's why we don't see the same amplitude, like a strong amplitude. Okay. Just to be able to compare to the harmonic noise, I also checked different frequency of the oscillation in this deterministic case, and we saw similar to the previous case that for small oscillation frequency we have suppression of tunneling, and for values of more or less equal to 2 omega Bloch, we have enhancement of tunneling, and then here we have the regime where the effective model is valid. Then we just extracted the values to compare to the harmonic case. Here I just took one of the cases I showed for with the harmonic noise with the variance 10, and then we did calculation for 2 of these omega 0 with the deterministic phase, and we see that it actually can predict or it lies very nicely on top of the results from the harmonic case. So therefore we could introduce 2 benchmarks to our system. One was this deterministic case, the other is this effective model. And more or less it gives us so basically I'm able to control parameters and then know that what parameter at which regime gives me what effect. And also I can introduce benchmarks to predict in different regime the behavior. And by this I just conclude. So I showed you that we are able to look at the full dynamics of the Landau-Zener transition, and that's why we see the step structure. Then we are able to control the decay of this survival probability or control the tunneling by changing system parameter like force or the amplitude of the lattice. We could change the initial condition, so the width of the initial momentum distribution. We can control the atom-atom interaction and then see the impact of it, and then we are able to do calculation in different bases. I said in the beginning whether we are able to control the decay in the time-dependent and stochastic potential. Now, looking at my result, I can say yes, we can control the tunneling, changing the parameter of the noise, and we are able to see enhancement and suppression of tunneling in a controlled way. And I introduce effective model and oscillatory phase as a benchmark for our fast noise, and more important than that, we introduce a scaling, which makes us able to reduce the parameter dependence of the system and see a universal behavior of the observable in the system. So we have as you see, we had a lot of parameters and a complicated system. Nevertheless, we managed to control everything, analyze the dynamics in a very good way, and in agreement also with experimental measurements. For future, there are possibilities to extend it. One is, so if you remember, due to repulsive atom-atom interaction, we had enhancement of the tunneling. Also, due to stochastic potential, we are able to see enhancement of tunneling. Now we can mix these two and study the interplay of the atom-atom interaction and the stochastic potential, and see whether these two effects may cancel the effect of each other, or they enhance the effect of each other, so we can see a suppression where we will see the enhancement. The second thing one can think of is use the noise in the two-state Landau-Zener model, and then find an analytical model for the tunneling probability. Some work has been done in this part by some other people, but still there is a space to go much more beyond. And then I would like also to use the stochastic process and what I learned there, and then apply it to some other models and other problems. And by that, I thank my collaborators, my supervisor, Sandro Wimberger in Heidelberg, and Ennio Arimondo, head of the experiment in Pisa, and Riccardo Manella, which is a noise expert in Pisa, also helped me for the noise part. And this is Heidelberg, and I thank you very much for your attention.
There was one question. The moment that you discussed the nonlinearity effects and so on, it was not clear to me, because you have this coefficient, the Brodsky-Tayebirad in the nonlinear terms of this coefficient. It was not clear to me whether you are considering the attractive or repulsive case, or self-focusing, the focusing, or you consider both.
You can
signs.
consider basically both, just changing the sign of the S-plane, the scattering wavelength. But in the plot I showed you for the survival probability, it was repulsive.
And repulsive is what I understood.
Only in the decay plot I showed you, there was one calculation for the attractive.
Because your conclusion was that the nonlinearity was somehow smoothing out, and it was like defocusing the resonance. So I'm curious whether, I mean, a self-focusing and attractive nonlinearity, to me, I mean, could have some interesting non-trivial effects that, I mean, more than just smoothing out, more creative roles. So I don't know if you thought of that.
We have done, I mean, theoretically it's possible just to consider the attractive interaction, but experimentally it's very difficult, because then the system collapses and the BoseEinstein constant is not as stable. There are some type of atoms that one can study the attractive interaction there. For the matter of experiments, it's more convenient than repulsive, but of course people now are studying the attractive calculation, and they are seeking interesting phenomena can happen there. I mean, there might be more interesting physics there also, because basically it's just contracting the wave pattern.
Yeah, there is a related question. So in electronics, super lattices is very important to take into account the interaction, because this produces, for instance, domains of different regions with different electric field strength, or you have self-constrained oscillations. So in your system, do atom-atom interactions affect the potentials? Do they have the lattice potentials?
Effectively, yes. So there are some, if you do the perturbation theory, and some people have done it analytically, and they found out that basically the effect of interaction is modifying the band structure, and the band gap is changing. So when you have repulsive interaction, the band gap is decreasing, and that's why you have enhancement of tunneling. So it's changing the structure of the potential.
And it is kind of a self-consistent way. I mean, because this automatic interaction depends, of course, on this probability, right? On this psi square. And this probability, if the potential changes, may also change.
Yes, it's time dependently changing.
Yeah, independently.
Yes, it's changing in time, but so how it changed? So, okay, that one affects the observable, but the potential will be affected as a not time dependently. It's a constant value. So you only renormalize, you can neglect the interaction, for example, and then renormalize the amplitude of the lattice. So overall, it's like if you have a lattice like this, then for repulsive interaction, the amplitude of the lattice is smoother. Effectively.
So it's a small effect.
Yes. But the time dependence only comes when you want to look at the survival probability. But I don't think that time dependently. Okay, now I think of it, it can affect because the strength of interaction is changing and then the value is changing. Yeah. True.
Any further remarks?
With this stochastic phase in the potential, you get a number of interesting effects. But what was, in the first place, the motivation to introduce it?
So one motivation is basically, I mean, people experimentally, they are using disorder, and disorder exists everywhere. That's why people are interested to introduce the disorder and therefore have more realistic system. It can be disorder lattice, or it can be some other type of disorder in the system. Then there is always a phase difference between the two lattices, so in the disorder system. There could be other signals also in the realistic system. That's why we decided to have a time-dependent phase between them, because one should be considering also the changes happens while the experiment, you're doing the experiment in the phase shift.
Can you tell us something about thermal effects?
Thermal effects. In which one?
Temperature.
Temperature. So basically, in the for the first part, the BoseEinstein condensate we had, the temperature is very low. So it's almost zero. It's very important to have a very low temperature.
But it is not zero.
It's not like 50 nanokelvin.
Yeah.
You cannot go more.
No, my question is, are there small thermal fluctuations important?
If you increase the temperature, yes, you see some instabilities and some effects of the temperature. And for example, I mentioned that where we studied the width, the change in width of the momentum distribution, that's actually it's related to temperature. If you have larger temperature, higher temperature, then you have larger width of the momentum distribution, and that affects the tunneling probability.
So do you reach a regime of competition between quantum tunneling and thermal enhanced tunneling? Or?
Thermal enhanced tunneling?
Yeah. Thermally activated.
Yes, one can. I mean, I didn't go to that regime since I was always in the BoseEinstein condensate regime. But if you go in the regime that you have a thermal gas, then you see exactly the exponential tunneling behavior. So you have, I don't know if it is enhancement, but
without distortion.
Yes. But in the noise case, if you have a larger T, which also is related to temperature, then you have enhancement. Yes.
Okay, now are you familiar with this ratchet stochastic thing?
Yeah, more or less. I mean, I'm not personally working on it, but
having worked with Ricardo Manel, I'm sure that you have heard about it.
Yeah.
Now, is that something that one could study here? I mean, you have a tilted potential, and you can make it time-dependent.
Sure. I mean,
has that been done, or?
Not with this. I just go back just to make it. So if you look at this potential, So this is very similar to the driven, harmonically driven. The works have been done experimentally, also theoretically, considering one lattice with the harmonic phase. And if you do the gauge transformation there, you will have the linear dependence on the force with the time-dependent cosine factor. And there, this means that if you have, till now we had a constant tilt, considering the factor of cosine, you will have a changing tilt for the potential. And actually, Ennio and Mondo, separate from this project we had together, they did experiments for such a case. And there they see the Bessel function for the tunneling behavior.
Okay, but do they see a noise-induced motion of the unit? But very good.
I think there's no issue.
Well, there are two signs, right?
And has that been analyzed theoretically?
Yes, the one potential with the harmonic phase, yes, has been studied theoretically by, I forgot his name, but some guy in Innsbruck, Augsburg.
In Augsburg?
Yeah, Augsburg.
There can be.
No, not him. A Holthaus, Martin Holthaus. He theoretically studied such a potential. I mean, of course, considering the harmonic driven part.
We can continue with lunch. Okay. So let's thank Ghazal again.